kind of difficult to grasp. So I was thinking of diving deep into that, but I think if we do that, then we might have to sacrifice another topic. So I think maybe I just kind of want to mention it, and let's see how it goes by mentioning it without really doing too much with it. Last time we ended with finding the arc length of a helix from 0 to 2 pi, and then we have this arc length formula. And then one of the things that I mentioned as we were talking about the arc length formula is that there's an infinite number of ways to parameterize anything. And yesterday I wrote a couple of ways to parameterize the same helix with different boundaries. But there's one special way to parameterize something, any curve, so that it's called parametrizing by arc length. So what that means is that you set up your parameterization so that when you use the formula for finding the arc length, your parameterization will just be the length of the thing that you're looking for would just be the top limit. In other words, or for an example that we were doing yesterday, if we have r of t is equal to our helix, we want to parameterize this in a certain way, and the way they discuss this parameterization is that they change the variable. So we'll call it r of s, and I'm just going to put stars there for now. Maybe we'll think about trying to solve for this, but want to put this parameterization so that when your s value goes from 0 to whatever, let's call it a. I don't know if we should call it a. It's going to confuse things. C. Then that means if we take this parameterization, the length of a curve from 0 to c so notice the variables. The variable that I'm using is with respect to s, that this is just going to equal to c. Now, practically, when I say practically, I mean like as a working example, finding this new parameterization would be really, really difficult. It turns out that with a helix, it's not so bad, and we could probably do the work, but I think the book does it for you, so you can check the book to see how they reparameterize the helix so that it's parameterized by arc length. But the idea here is that you're making the parameter t be dependent on the arc length, or the arc length is dependent on the parameter t. I guess I should say it that way. Yes?
In what cases would we have to use this technique?
Well, that's what I'm saying. In practical terms, you probably don't really have to use it. Something that would be nice to have some sort of visceral idea about, so that when we talk about some of the other things that we're going to talk about, we can just mention that it can be parameterized by arc length, and then we can kind of see a picture of that and then work with it. So let's see what my notes say about this. This kind of shows a little bit more information about reparametrizing by arc length and stuff. But let's just say whenever I mention parametrizing by arc length, then that just means the variable t becomes the variable s. And then the length that you're measuring is dependent only on s. I wrote this a long time ago. I don't know if I remember what it means or what it says. Oh, this is for a circle. So if I have a circle that's being parameterized regularly, the regular parameterization would be like cosine t, sine t, right? So the left-hand side is being what's called parameterized by arc length. And no, I'm sorry, the right-hand side is being parameterized by arc length. The left-hand side is being parameterized by just the regular parameter t. So you can imagine this left-hand side is that cosine t, sine t. And the right-hand side is adjusted so that it's parameterized by arc length. What that means is that if my parameter, so this is the value, these are the values of my parameter here, and these up here are the values of the arc length as I'm moving around my parameter. So with a regular parameterization, if my parameter t is at 1, when t is equal to 1, I can see that my arc length here is 5. And my arc length over here is 1. So if I put a value like pi, so if I put a value of pi here, my arc length is 15.7 if I would just regularly parameterize it. And if I had parameterized this by arc length, then my value here is 3.14, which is pi. So the idea is that the parameterization by arc length would trace out the curve and measure the arc length. And the measure of the arc length is going to be the same as the measure of the independent variable. So I think this is the parameterization by arc length over here. So let me just put this down as an example in our notes. And we'll specify that this is a regular parameterization on this side. Well, your R of t is equal to, this has radius 5, so I'll put 5 cosine t 5 sine t. And this is your parameterization by arc length. And this, I'll use the variable s to represent that it's parameterized by arc length. And this is going to be 5 cosine s over t. Oops, sorry, s over 5. Uh-oh, my 5's and s's. You know my s? Five sine s over 5. So the arc length that's measured over here is the same, is equal to the parameter. And if we look at the parameter as being s, then that's what we'll call the parameter. So it's equal to whatever the parameter is. Whereas on this side, when t is equal to pi, your arc length equals 15.708. So that's what? Say it again? This is 5 pi? Wow. So it turns out that circles and helix curves, those are nice to play around with in terms of getting some arc length information down. All right, I think we've talked a little bit too much more than I wanted to about this stuff. So let's move on to our next topic is curvature. Yeah. Just for now, let's just say it's magic. It comes from finding the arc length of the original curve with the parameterization and doing some setting it equal to each other kind of thing. And it works nicely for circles, but like I said, if you go out of if you don't do a circle, then things are going to get a lot more confusing. All right, parameterizing by arc length. So our next topic is, well, it's within the same section. Our next topic is the curvature. So guess I could have just wrote this. curvature. Let's go two-dimensional first, and then we'll extend it to 3 dimensions, or we can pretend it's a 3-dimensional curve where z is equal to 0, but this could be extended. I think it's kind of easier to start looking at curvature in 2 dimensions first. So if you look at a curve, this is just some random curve. We can take a look at some points here. Let's sample a couple of points. Let's sample this one, looks interesting, and maybe this one over here, and maybe this one over here. Now, at each of those points, we see something. We can talk about some distinctive properties about those points. And one of the things that we can talk about is kind of like how curved they are, right? So the idea of curvature is to look at a point on a curve and imagine how much it bends. So how can we measure how much something bends? Well, what we could do is we can take a look at a tangent vector. Actually, tangent vectors are a little tricky because the length of the tangent vectors make a difference. And since you can parameterize things any way you want, these lengths of the tangent vectors can be long and short and can be a little confusing. So what we're going to do is we're going to take a look at the unit tangent vector. Because if you take a look at the unit tangent vector, then we know that it's going to have unit length. And we're going to be a little bit more focused on the idea of the direction more so than the length of the tangent vector. So that's why that first thing that says under this is a unit tangent vector. So the unit tangent vector is basically the velocity vector divided by its magnitude, just to make it a unit length. Now, what we could do is at some short amount of time period over here, you can imagine moving to another point and finding the unit tangent vector there. So if we take a look at this first example over here, our unit tangent vector, how much is our unit tangent vector going to change? Is it going to change a lot or a little? It seems like it's going to change a little. It has the same length, so the length is not going to matter. So the direction that it's moving, a little bit over that, it's going to move almost the same direction. So there's very small changes there. How about this one? If we go to this a little bit off of this tangent vector, it's moving a little bit more, right? It has a little bit more change. And then this one over here, this one has a larger change. So it looks like intuitively we can think about the change of the unit tangent vector, the rate of change of the unit tangent vector. So if we can somehow measure the rate of change of the unit tangent vector, that's going to give us some idea of how much it's curving. So the unit tangent vector and the change of the unit tangent vector looks like we're going to be dependent on a vector, right? Since we're throwing away the idea of its magnitude. So we're a little bit more concerned about how it's changing its direction. But when we're trying to quantify this, we really just want a scalar value. So it looks like the thing to do might be to find the rate of change of the unit tangent vector, and then, I don't know, maybe find the magnitude of that with respect to the arc length. So if we're going to find this rate of change with respect to the arc length, that's going to give us a nice number that describes its magnitude. All right, so let's see. What do I have in my notes? If we imagine the velocity vector riding along the curve, we can measure how much the velocity vector changes. And I already said that. Should I copy this too? I suppose I should. So the main formula for this is looking at how the unit tangent vector changes with respect to the arc length. Now, because unfortunately I've mentioned that the whole idea of figuring out the arc length is kind of difficult and kind of hard to deal with, this first definition is not a very good working definition for us. So it turns out that this other definition is a better working definition for us. And this first formula that they have there would just be some intuitive sense of what or with how to measure the curvature. By the way, the curvature, they use a little Greek letter K, kappa. So this is kappa. So as a function of t, we're going to use this formula where we have to find the, what do you call it? The unit tangent vector. Take the derivative of the unit tangent vector and divide by basically the arc length, the length of the velocity vector. All right, so let's see if we could do an example. Let's try I don't know what we should try. Let's try a helix. Seems like it's the thing to do. And normally we would want to find out the curvature at a particular point. I mean, we can find the curvature function in this particular formula. That's what they say. It's a curvature function, t. But we can also find the curvature at a particular point. But as you can see with the helix, think about the helix. There's like, how would you compare the curvature at one point on the helix versus another point of the helix? Think about a spring and think about the curvature of that. What do you think? Do you understand my question? The question was, if you look at 2 points in the helix, what can you say about the curvature between those 2 points? They're constant curvature, right? Because if you look at a spring, the way the spring curves at any point looks like it's going to be the same. Now, not like this example that I just drew up. The curvature at some points look like they're a little bit more drastic compared to the others. So So if we compute the curvature here, we should expect it to be constant. Let's see. We need r prime. So it's sine, negative sine t, cosine t, and 1. We need the magnitude of r prime, which is the square. We did this already, right? Square root of sine squared, square root of cosine squared, or square root of sine squared plus cosine squared plus 1, and then we ended up getting 2. Can I just write that? So t is equal to the r prime divided by the magnitude of r prime. So for that, I'm just going to put the magnitude of r prime as not as a denominator, but I'll just think about multiplying this by a scalar. And so I want the derivative of this. So that's what this top part is saying. I want the derivative of this. And because this is a constant, I'll just leave the constant out and take the derivative of the inside. So derivative of sine, negative, derivative of sine is cosine, but it's negative, so it's negative cosine, negative sine, and 0. So that's my t prime, and then if I want the magnitude of that, the magnitude of the cosine-sine combination is just going to be 1, and I just have an extra scalar out there, so that's whatever that scalar is going to be. So I skipped a few steps with finding magnitudes, but you guys can work that out if you want to. So the curvature now that we're going to come up with here, if we put all this stuff together, kappa of t is equal to 1 over the square root of 2 divided by square root of 2. So I think it just turns out to be 1/2. Is it 1/2? All right, maybe you should check my work. Does that look right? No? What? I think it should be 1. Is it 1/2? Did I do these magnitudes correctly? Okay. I hope that's right. Yeah. T prime? I think that's what I meant to write. All right, well, if it's right, it's right. We can move on. It's probably not right, but we'll move on anyways. All right. So turns out that there are other ways to redo this formula, to adjust the formula. And there's another way where you don't have to look for the unit tangent vector. You can just do this cross product. I don't know if this is more convenient. But I guess for some cases it could be more convenient. If you have zeros or something, maybe it might work better. Who knows? Let's see if we can make one up. What would be a good? I don't know if it's a good one. Oh, the really popular one that they do all the time is the parabola. Find the curvature of the parabola. Let's do this as an example, and then find a more specialized formula for the curvature if we're talking about in 2 dimensions. So curves in 2D of the form y is equal to f of x. And normally we've been putting formulas up and then we've been doing examples, but let's try to see if we could do an example out of this. For example, y equals, let's do natural log, ln x. So I can only put in numbers that are positive. I can't put 0. I can't put negative numbers in here. So let's see if we can find a formula for finding the curvature for this. Now, we've been dealing with parametrized curves, right, or vector curves. So the first thing I might want to do is write this as a parametrized curve. Let's just say r of t is equal to, you guys know the trick for writing a function like this, relation between x and y, as a parametrized curve? X is equal to what? If you let x is equal to t, then that's like your independent variable. And then your y is going to be equal to whatever the function is. Except I would put t in there instead of x. Now, we have formulas for 3 dimensions. So if we imagine this in 3 dimensions, we can just look at this as if it was flat on the xy plane. And so let's just say z is equal to 0. So now I'm looking at this formula over here. This might be an interesting thing to use for this particular case because I have something that's flat on the xy plane. And so let's see how this will work out. So I'm going to want r prime and I'm going to want r double prime, it looks like. So let's find r prime of t. So the derivative is 1 comma 1 over t comma 0. And then let's find r double prime of t. 0, negative 1 over t squared, 0. So I'm interested in crossing this. Normally, I'd want to try to stay away from the cross product, but I have a bunch of zeros here, so this actually might not be so bad. So let's find the cross of this, r prime of t cross r double prime of t. All right, I have them laid up on top of each other already, so I can pretend there's an I, j, and k in the first row out of this and make a matrix out of it. So in the I, I have 0 and 0. In the j, I have 0 and 0. See, that was kind of nice, right? If you think about crossing 2 things that are flat on the xy plane. If they're flat on the xy plane, when you cross 2 vectors, remember they're supposed to be perpendicular to those 2 vectors, right? So immediately you can see that the x component is 0, the y component is 0. This thing's just going to be going straight up or down. And so you have 0, 0 for the x and the y, and so the only thing left to do is find out what's happening in the z. So in the z, I got negative 1 over t squared minus 0. So that was a simple cross product. So the magnitude of this goes in the numerator. The magnitude of this goes in the denominator. So let's find magnitudes. So the magnitude of r prime of t cross r double prime of t is equal to, well, it's just this thing squared under a square root, so it'll just become positive, right? So put a square root, 0 squared plus 0 squared plus negative 1 over t squared quantity squared, and under a square root it'll just become positive. And then the magnitude of this is the square root of 1 plus 1 over t squared. So we put those two things together and we should get our formula for kappa. Not a vector. So the cross product stuff goes in the numerator, and the r prime magnitude, oh, this has to be taken to the third power. I guess that would be 3/2 or something. Now, if that's all they're looking for, then you could be done, simplify it. But if they want you to simplify it, I suppose you could try to simplify it. Maybe it will be good for this. Okay. I think one of the questions, and it might be in your homework, is they ask you to maximize the curvature. So this graph, you know, is an ln function. It kind of just looks like this. And if you want to try to maximize the curvature, you want to see which of these points has the biggest curvature. So let's see if we can answer that question. Let's try to maximize the curvature. How do you maximize the curvature? How do you maximize anything? You remember that back in Calc 1? Yeah. Find derivative set equal to 0. Remember that business? Maximizing, minimizing. So the curvature is what we want to maximize. So we basically find kappa of t, or kappa prime of t equal to 0. And then, you know, check first derivative test or whatever to make sure that that's your maximum. So given that idea, I may want to simplify this. Or I may just want to use a computer to solve it for me. Let's see if we could simplify it. We're math people here. So the kappa, I guess the t squared goes in the bottom, and then I have to, if I can, try to filter it in here, right? 1 plus 1 over t to the 3/2. If I try to match the 3/2 power, that would be like 6/2? 6/3? Why don't I just have my computer do this? I want to put everything into one parentheses. How do I do that? Can I do that? No? All right, fine. All right, I have Mathematica open, might as well use that. So my kappa is equal to 1 divided by t squared, 1 plus t to the, I guess that's 1 over t. Halves power t squared. All right, let's see. All right. Right. So we don't want to deal with negative numbers because the ln function doesn't exist on the negative side. So let's just say we got our results that we wanted. And we can say that when t is equal to positive 1 over square root of 2, then we have the maximum value. So if you look at that in your curve somewhere, it'll probably be, this is 1, square root of, what's 1 over square root of 2? Is that less than 1 or bigger than 1? I guess this is root 2 over 2, right? 1 over root 2? It's less than 1? So this point over here, some point over here will give us the largest curvature. That's the most curved part of the natural log function. All right, questions? So this is the formula that we actually could have used if we have this special case. So if we consider something in 2 dimensions, then this formula is something that we could have used and probably would have been a lot easier than having to cross a couple of things. Although crossing those vectors with zeros in them wasn't too bad. But in any case, this kind of turns out to be a little bit easier to deal with. So let's do another one real quick since we have this formula up. And actually, let's use this formula. Let's do that parabola y is equal to x squared. If you imagine how a parabola looks like, it looks like the vertex is going to have the maximum curvature, right? And then anything outside of that will be a smaller and smaller curvature. So, according to our curvature formula, we need things like the first and second derivatives. That's easy enough. That's 2x and 2. So according to the curvature formula, kappa of x is going to be 2, the absolute value of 2, divided by, I guess this is a parentheses, 1 plus the derivative is 2x. And the 2x has to be squared. And then this is raised to the 3/2 power. Uh, 1 plus 4x squared to the 3/2 power. So if we maximize this, we'll see that the maximum value will happen at x is equal to 0. Okay. Now there's something else really kind of interesting about this that I want to tell you about. And this curvature is tied in with this thing called a tangent circle. Let's go back to my other drawings over here, my first drawing. Let's take a look at this really tight curve over here, which we would imagine has a large curvature, right? If we take a look at that tight curve, we can imagine at that right at that point, that red dot, there's going to be we could draw a circle that's tangent to that red dot. This one over here, this one looks like it's a larger circle. So we got a large curvature and we got a small circle. We got this curvature over here and we got this circle. Now we got a small curvature. How do you think the circle is going to look like? The circle is going to be bigger. These tangent circles. So there's a relationship between those circles and these curvatures. It turns out that if you were to find the radius of these tangent circles, the radius is going to be the reciprocal of the curvature. So we'll say that over here. We'll draw a tangent circle over here. It turns out that the radius of the tangent circle is the reciprocal of the curvature. So that's an interesting relationship. So if you have a large curvature, you're going to have a small circle. But that kind of makes sense, doesn't it? Yeah? They have an inverse relationship. So let's find the curvature at 0. Let's put 0 in for x. If we put 0 in for x, I think that's just going to be 2. Right? So that's going to be the curvature of the parabola at 0. Which means a tangent circle has radius 1/2 at the origin. Well, if we draw more stuff here, if we imagine this curve being drawn from left to right and would have a tangent vector going in this direction, then if we find a perpendicular vector, a vector that's perpendicular to this tangent vector, then we can know which way the direction to go to get to the middle of the circle. So finding a normal vector, a vector that's perpendicular to your tangent vector, would be another interesting task for us to do. But in this case, in our simple example, it looks like the normal vector is just going to be going straight up, right? So normal vector is equal to 0, 1. So if we go in that direction, and give it a radius of 2, or I'm sorry, a radius of 1/2, then we can find the equation of the circle. So it looks like it's just going to be on the y-axis, and if we just go as far as 1/2 with a radius of 1/2, then we can find the equation of the circle. So equation of the circle for us equation of the tangent circle is going to be x minus 0 squared plus y minus, remember the center is going to be at 0, 1/2. Y minus 1/2 squared is equal to 1/2 squared. So that's interesting. That means if I draw the parabola and I draw that circle, it should be tangent to that circle. Let's get my other program going. So here's my parabola, my tangent circle. Should be right on that parabola, touching it at 0 at the origin, and then it has radius of 1/2. So what if I was interested in finding the tangent circle at 1 or something? So if I was interested in finding the tangent circle at 1, so k of 1 will give us the radius of the circle, but how do we know which way to go? So let's get that set up. Yeah, we're going to need a normal vector. Tangent, vector, tangent circle. So the kappa is not such a big deal for us. We can easily find that. Do you remember what the formula was? I think it was 2 divided by 1 plus 4x squared to to the 3/2 power. So when x is equal to 1, this will be 1 plus 4 is 5. 5 to the 3/2. So the curvature over here will be 2 divided by 5 to the 3/2 power, whatever that is. It's probably something less than 2 for sure. Less than 1, it looks like. So it'll be a smaller number, which means the reciprocal of that will be a larger radius. So the radius of this thing will equal to the reciprocal of this. But what we need to do is we need to find the normal vector. A vector that's perpendicular to our tangent. Now, there's two possible normal vectors happening here. One's going in and one's going out. We want the one that's going in. And so it turns out that this normal vector is going to be kind of on the same side as the acceleration. Do you guys know what the acceleration is for a parabola, by the way? So acceleration for a parabola turns out to be second derivative, right? Take the derivative and it's going to be some constant function that's going to be going in the same direction. It's going to turn out. But that's at 1, that's clearly not going to be perpendicular. It's not going to be a normal vector. So how are we going to find a normal vector? We're going to find a normal vector by I don't know. We're going to find a normal vector by projecting. If you take a look at your velocity vector, your tangent vector, and more specifically, if we take a look at this as a unit tangent vector, I'll just call it t. And then your acceleration, whichever side your acceleration is going to be on, if you project your acceleration onto the tangent vector, the projection actually gets us this value going along in the same direction as the tangent. But what we really want is this vector right here. We're going to want that vector, and then we're going to want to stretch that vector to have unit length so that we can just multiply it by the reciprocal of this thing. So there's a nicer formula for this. Oh, yeah, okay. Let's see. So it turns out that if we take our unit tangent And then we take the magnitude of this thing. This is actually equal to 1, right? Because it's a unit tangent vector. So we want another vector that's perpendicular to this. It turns out that if we rewrite this, this is the same thing as t of t dotted with t of t with a square root. Is that right? So if we square both sides, we have t of t dotted with t of t is equal to 1 squared. That didn't change anything. So here's the trick to this whole idea. We're going to take the derivative of this thing with respect to t. Now, if you remember in the properties page, the derivative of a dot product is like a product rule, right? So it turns out that this derivative is t prime of t dotted with t of t plus t of t dotted with t prime of t. Now, if we take the derivative of the left-hand side, we have to take the derivative of the right-hand side. Derivative of 1 is equal to 0. And it turns out that since the dot product is commutative, you can switch the order, which means these two things that we're adding are exactly the same. Oops. So the dot product of t and its derivative t prime is equal to 0. So it turns out that t prime of t is actually perpendicular to t of t. Now it looks like t and upside down t. So it turns out that those two things are perpendicular, which gives us a good candidate for our normal vector. So to create a unit normal vector, we can just use t prime. But t prime, when you take the derivative, it might not be of unit length anymore. So to just make sure it's unit length, you have to divide by its magnitude. So we'll call this capital N with an arrow on top. That's the normal, unit normal vector. This is t prime of t divided by the magnitude of t prime of t. And all these t's over here should have arrows on it because it's a vector. So what we're going to do is we're going to use this next time. We're going to use this to create our tangent circle for this particular example. And then we'll carry this on over to 3 dimensions because we did this in general terms. This could have been in 2 or 3 dimensions. So this should work in either case. All right? Okay, next time.